So in this lab, I had you look at three factors that impact the rate of electron emission as a result of the photoelectric effect. We were taking a look at how light can cause metals to eject electrons. One of the first factors to take a look at then was brightness or intensity. And if you're a need to write down vocab person, here's one you should know. A good definition for intensity is that the intensity of a light is proportional to the number of photons of light hitting a particular surface any given second. So let's say I freeze this moment of time. There are 3 photons of light incident on this potassium surface. So the brightness of that light or intensity of that light is proportional to how many photons are hitting it. So I'm going to use this simulation to help you picture brightness or intensity of light. And even though it's not the same simulation experiment you were using, I like this one because it shows you that intensity is not only the brightness of the light, right? And in this case, the light is impacting the metal, and the metal releases the electrons. Okay? But we can also put on photon view. And so we see that a low intensity means fewer photons are hitting this metal, and that high intensity means a lot of photons hitting this metal. And the more photons you have, the more collisions could knock an electron off that metal to complete the circuit and send a current through. And if you're thinking about the photoelectric effect in terms of their solar panel application, of course this makes sense. Having brighter light means more photons. More photons means more electrons. So by increasing the brightness or intensity, we get more electricity out, which we know practically is why setting up solar panels in Iceland wouldn't be a very great idea. Of course, we know that the brightness of light isn't the only thing that impacts the number of electrons that come out. With the yellow, low-energy photons here, you can send as many of these as you want at a metal. These yellow photons don't have enough energy to dislodge an electron from that metal, to overcome the electron bonds to the atom. And so photons that don't have enough energy don't emit electrons. And conversely, photons that do have enough energy could emit electrons. So let's look at this simulation again. I've got the intensity all the way up, but no electrons are coming out. Well, that's because these long wavelength infrared photons just simply don't have enough energy to dislodge the electrons from the sodium metal during these collisions. So I'm just going to slowly shorten the wavelength, increase the energy going through Roy G. Biv, right? And at some point, we find that there is a color at which electrons start coming out. Oh, there it is. The electrons started coming out. This 532 nanometers for the sodium atom must be the minimum amount of energy needed to cause electrons to break that bond with the atom and get released. If I put in more energy than green, like let's say violet, the electrons that came out because of the violet collisions have more kinetic energy and reach the other side faster. So let's put some ultraviolet in there. All the extra energy that these photons has turns over to kinetic energy of the electrons. So I know that the energy from the photons has to overcome a minimum threshold for the electron to escape, and whatever energy is left over after the escape turns into kinetic. So we still have conservation of energy. So then we get to our third factor, the type of metal. I've changed from sodium metal over to copper. Wouldn't copper be great? Copper's a conductor, it's got loosely bound electrons. Let's check. As I increase the energy, decreasing the wavelength here, okay, so I haven't come up with a color yet. Passing green. Even with the blue doesn't have enough energy per photon to dislodge an electron from copper. We need to find that minimum energy needed in order to cause electrons to come out. There we go. So copper and sodium must be different in some way, and we call that way the work function. The different types of metals have different work functions. They require different amounts of energy needed to remove an electron from an atom. So sodium only needed green light. Each green photon had at least 2.28 electron volts of energy. So once we had more than that, the electrons could escape the bonds and be ejected using the photoelectric effect. But for copper, I needed to put in ultraviolet light. It needed to have more energy. It needed to have more energy in order for the electron to escape that atom. So think to yourself, which one do you think would be the absolute worst metal in this chart for making a solar panel? Just eyeballing this, it looks like it would be platinum. Right? With platinum, it would take at least 6.35 electron volts to get any electrons out, whereas something like sodium only takes 2.28. So here's why. Imagine I'm looking at sodium versus iron. I drew in their two work functions, and sodium only takes 2.28 electron volts in order for an electron to escape the ground state of this atom. So if I have green light with 3 electron volts of energy come in and hit this electron in a collision, it will use 2.28 of that electron volts to escape the energy well, but the remainder of that energy is the kinetic energy. And if you're a math person, can you imagine how much in your head? How much kinetic energy does this one electron have here? Well, if 3 electron volts came in and it took 2.28 to escape, this one must have 0.72 electron volts of kinetic energy left over. And that's energy that could be used on a solar panel to power a grid or power your house. But if iron was used for your solar panel, 3 electron volts would go in, but that electron wouldn't come out. It would only get partially up the well, with no energy or electron emitted. These two metals must have different work functions and a different related quantity. Because each of the metals has a different work function, each of the metals also has a minimum threshold frequency. That's the minimum frequency needed in order to have an electron be emitted from photoelectric effect. So, for instance, in this graph, imagine that these low frequency waves are completely unable to start emitting electrons, and right at 1.5 times 10 to the 15th hertz, electrons start being emitted, and all that leftover energy becomes kinetic energy. So, for tonight's homework, finish up the rest of these comprehension questions, and for tomorrow, we'll get into how to do some of the calculations behind these. Review Wednesday, test Thursday, and then spring break. Maybe I'll go to Aruba. Best of luck.